Want to slash your transformer training time without sacrificing even a fraction of a single % of model accuracy? The method requires extracting high-performance fused kernels from NVIDIA Apex and pairing them directly with modern PyTorch. This chart compares standard PyTorch throughput against our target Apex setup, aiming for that massive jump. To achieve this, you need 4 things: a compatible GPU, PyTorch, the CUDA toolkit, and crucially, C++ build tools. Skipping those C++ tools guarantees the installation will quietly fail. Let's get the setup right so we can actually utilize the hardware. The most common trap with Apex is the silent fail. A standard pip install might look successful in the terminal, but it actually defaults to a Python-only setup that completely lacks hardware acceleration. To get the actual performance gains, we have to clone the NVIDIA repository and build the library directly from source. When running the setup script, you must include these 2 specific flags, --cpp_ext and --CUDA_ext. Those force the compiler to build the high-performance extensions. Once the build completes, we run a short Python detection script to query the environment and confirm which fused kernels are actively available. Without those compiler flags, your script returns false for FusedAdam. With a proper build, the system recognizes the CUDA kernels and marks them as available. Confirming kernel availability up front prevents you from running a 10-hour training loop with 0 actual performance gains. To see what these kernels actually do, we will test the optimizers. We set up a test model packed with linear layers to intentionally make the optimizer's computation time highly visible. Implementation requires swapping standard PyTorch AtomW for Apex's FusedAdam. As you can see, the initialization syntax remains nearly identical. We push the exact same dummy data through an identical step pattern for both methods. This isolates the optimizer, allowing us to measure only the update speed. Looking at this bar chart for step times, standard PyTorch completes its updates, but the FusedAdam implementation cuts that time down, delivering a clear percentage speedup right out of the gate. Standard optimizers iterate through tensors one by one. FusedAdam combines these updates into a single multi-tensor operation, drastically reducing memory reads and writes, so the optimizer is no longer your bottleneck. We apply that exact same logic to our normalization layers. We generate a massive tensor shaped to represent the hidden states of a typical transformer model. Speed means nothing if the math is wrong. Before relying on FusedLayerNorm, we have to verify that its output perfectly matches standard PyTorch. We initialize both normalization layers and copy the exact same weights and biases to each. Then we process the tensor through both layers and calculate the maximum absolute difference between their final outputs. As this console readout shows, the maximum difference is exactly 0.0. The math is identical. This split chart tracks the microsecond latency for both passes. FusedLayerNorm consistently clears both the forward and backward passes in a fraction of the time. Apex also includes FusedRMSNorm, meaning you can apply these exact optimizations to modern Llama-style architectures. By swapping in fused kernels, you accelerate computation on every single layer, without compromising the mathematical integrity of the model. Many developers make the mistake of following old tutorials and trying to configure mixed precision using the legacy Apex.amp module. PyTorch eventually integrated those scaling features directly into its core library. Native torch.amp is now the recommended standard for handling precision. Instead of wrapping your model in outdated O1 or O2 optimization levels, you simply use the modern torch.autocast context manager. Today's efficient workflow is entirely modular. Keep Apex strictly for optimizers and its normalization layers, letting native PyTorch handle precision. Step 5 is integrating everything into a full training loop. We start by building a standard transformer with attention blocks, embeddings, and feed-forward layers, running a baseline training pass in pure FP32. Next, we run that exact same architecture using our optimized pipeline. We slot in FusedAdam, apply FusedLayerNorm, and wrap forward passes in native PyTorch AMP. After both loops complete, we check the final loss values to ensure our optimized model actually learned the patterns correctly. This scoreboard visualizes the results. Baseline PyTorch metrics are set, but the fused Apex and AMP path finishes with a lower step time, pushing more tokens per second. Final loss values are identical, proving we sacrificed zero accuracy for this massive throughput spike. By properly installing the C++ extensions and selectively applying fused kernels, you maximize your GPU's utilization. You can find the full code for these benchmarks in the description below, and be sure to subscribe for more optimizations.